Welcome. In this video, we're going to define the concept of a Riemann sum, and this builds upon what we've already been doing in our previous videos. So if you haven't watched the previous videos on this playlist, I suggest you go back and watch them. In the previous example, we wanted to find the area of a velocity function that was not constant. It looks something like that, and we decided to use rectangles to estimate what this area was. In fact, we used 2, 4, 8, and 16 rectangles to estimate our area. Those are actually Riemann sums. So let's define more formally what a Riemann sum is and explain how to find these visually. The area under a curve on interval AB can be approximated by splitting the region into n subintervals of equal width. Those subintervals are then used as the base of n rectangles. The sum of the area of these rectangles is an approximation of the area under the curve. For n subintervals, the width of each rectangle is called delta x, and on the previous videos I just kind of put up on the screen what the width is, and this is how to figure it out. You take your maximum x value, so in this case it's b, you subtract your minimum value on that interval, and you divide by the number of rectangles you want, which is the same thing as the number of subintervals. And that's how you find the width, or that is delta x, of each subinterval. And so as a little mini example here, what are we actually talking about? Now say this here is my curve that I'm interested in, and I want to find the area of this region, and so I go ahead and break this up into n intervals. And so I should make it clear we have n intervals here. We need to figure out the starting point and ending point of each interval. How can we do that? Well, let's make a little sketch using a number line. Here's A, here's B. And let's break this up into n intervals. We're going to label the first one x0. So we're going to say this first left point is x0. And then this one is x1, x2, x3. And we're going to go all the way to b, which is xn. So then this one here is xn minus 1, xn minus 2. And that gives me n regions. So here's my first region, which will make a rectangle, second, third, and so on, all the way to the nth minus 1 region and the nth region. And that gives me the following. So my first interval is going to go from x0 to x1, and that would be this first interval here. The second interval goes from x1 to x2, and that's here. And we can keep going in this manner all the way until xn minus 1 to x sub n, and that would be this last region. And now this will help us when we choose to compute our sums using either left, right, or midpoints. So let's again draw our graph. And as you can see, I drew 3 copies of it, and that's on purpose. So now I'm going to draw some regions. So say this is my first region, second, and I'll stop there. So I know that this is actually x0. This is x1, x2, and so on, all the way to xn. And if I go ahead and draw a rectangle, if I choose left endpoints, then I'm going to go here to my leftmost value of the interval, which is x0, and I'm going to see how high that goes where it intersects with the graph. So this is the value of my left endpoint, that's f of x0, and that's of course assuming this function is f of x. And so here's my first rectangle that I've just sketched that uses the height of the rectangle as the function value evaluated at this left endpoint. And so I do the same thing for x1. x1 here, f has a value at x1 at about this height. And so this is where my next left endpoint is going to be f of x1, right there. And so I don't get us too lost in these labelings. I'll just go x1 comma f of x1. That's this height. And so that's my second rectangle. And now, again, I could have another rectangle here at x2, so this rectangle would be the same width, but of course, it goes off. We only really needed to see these two. And then I'm going to do one last thing. I'm going to change the color of this curve to purple, just so we can really see where it is in comparison to our endpoints. So those rectangles have a height that is equal to the function value evaluated at this left endpoint of the interval. So I would look for f of x naught, f of x1, and so on if I took the left endpoints. So if we're looking at right endpoints, I'm going to break up my intervals again. This one's x1, here's x2. A is going to equal to x naught, and I'm going to have a ton of other intervals here, and b is equal to xn. Well, rather than evaluate my function f of x at the left endpoint as I did here in this example, I'm going to evaluate it at the right endpoint. So I'm going to choose the height equal to x1 here. And so this rectangle has this height now. And here it is, f of x1. Then I'm going to do the same thing here for x2, where I take the height of my rectangle to be the right endpoint, which is x2, to get that kind of rectangle. So as you can see, this definitely changes, even with our rough sketch, what the rectangles look like. So we will get different areas depending on whether we choose left endpoints or right endpoints. Now, what about midpoints? Well, to find the midpoint of any of these intervals, you need to add these two values and divide them by 2. So in that case, we take the midpoint, which is equal to xi minus 1 plus xi divided by 2. So in this case, if this is x1, this is x2, this is xn, and we have a ton of intervals there that I'm not sketching. A is equal to our x naught, and then I'm going to quickly highlight this in purple just to be consistent. Then my midpoint, rather than choosing this left endpoint of x naught or this right endpoint of x1 as I did in these examples, now I'm going to choose a value right in the middle. That would be this height here. And then for this interval, it would be right about there. And my rectangles are going to be this tall now. And again, that would give me a different area when I use midpoints. And so for this first interval here, we'd compute our midpoints using this formula, where we would add up the max, the min, and divide by 2, and that'll give us this midpoint here, these mn's. And so that's one midpoint, here's another midpoint. In summary, to estimate the area under a curve, you can break the region into n intervals, find the width of these intervals in this manner by doing largest minus smallest divided by the number of intervals, and then you get to choose, are we looking at left endpoints, right endpoints, or midpoints? If you're looking at left endpoints, then you evaluate your function f at the leftmost endpoint. If you're looking at right endpoints, then you evaluate your function f at the rightmost endpoints. And if you're using midpoints, then you find the midpoint of each individual interval and evaluate your function f at that midpoint.